Hello everybody, I'm Michiel Hagedoorn. I work at Side Effects and I work on machine learning mostly and machine learning related tools. In this talk I'm going to talk about how you can build your own machine learning pipeline in Houdini using some tools. This talk is mostly focused on training on your own data, so it's not like using existing models, it's creating models from scratch using your own data. And the data can be synthetically generated in Houdini typically, but can also be handcrafted data. So this talk consists of 3 parts. I'm going to start talking a little bit about supervised ML. I'm not going to go necessarily very much into the Houdini nodes at that point. After that, I'm going to go into the Houdini ML nodes and how you create a pipeline from them. And then finally, I'm going to show you some applications that are built using this. Okay, let's start with the supervised ML. Machine learning has different flavors, and supervised machine learning is one of those flavors, and that's one of the flavors I'm going to talk about today mostly. Supervised ML is where you have inputs and outputs, and Houdini can be used as a supervisor in this. I'm going to focus mostly on regression. So regression is when you have continuous valued outputs. Classification is more like you have an output, like this is this kind of object, this is this kind of object. That happens in computer vision, but I'm mostly going to focus on continuous outputs. So what is regression? Regression is the problem of given a set of labeled examples, train a model that can predict the continuous output value for each input. I'm going to make this a little bit more concrete. So this is an unlabeled example. So we have a skeleton, which is an input to our system, but it doesn't have a ground truth associated with it yet. So this is a labeled example. Now we have labeled the unlabeled example. So the input is a skeleton, the label is a deformed skin, or more precisely the vertex positions of a deformed skin. Throughout this talk, I will refer to these 2 parts of a labeled example by input component and target component, and I'll usually use the same colors for this. I will use orange for input and green for target. Both the input and the target component consists of several shapes, or several tensors, I mean. And each of these tensors has a shape. A tensor is, I'm not going to go too deep into it, but it's basically a multidimensional array. So if you have a flat array of 1 dimension, it's a tensor of rank 1. If you have like a grayscale image, for example, you have a tensor of rank 2. If you have a voxel grid, you have a tensor of rank 3. So in order to better be able to discuss regression, we can look at a toy example, namely a neural height map. It's not always going to be a neural height map throughout this talk, but okay, it's a height map. So it's a function from points in a plane to a height value. So this is a nice example to look at because we know the entire function. We can visualize the entire function. In the applications we're going to talk out, this is not going to be possible at all because it's just not visualizable. How do you visualize a function that goes from volumes to volumes? You cannot look at such a function. But in this case, our inputs are 2-dimensional points, our outputs are heights, so we can observe the function in its entirety. But in real machine learning applications, we cannot observe the function in its entirety. We don't know it. So all we're given here is a bunch of input target pairs, labeled examples. So in this case, the labeled examples are like have an input component that's a point in the plane, and the target component is a ground truth height. We're going to look at 4 applications of regression in this talk, and the first one is ML pose correction. So this is a prototype we put together where we're fixing bad joint positions as shown in this picture. On the left, you see that there's an animated character which has certain issues around the knee and the toes, for example, and on the right is fixed. So in this particular use case, how would we model the labeled examples? The labeled examples could be driver mapping. The labeled examples could consist of an input that is a set of driver joints and an output that is a set of driven joints. So we have certain driven joints that depend on driver joints, and we create combinations to train a pose correction. Another example is the ML deformer we've had in previous versions of Houdini. And here we map a rig pose to a deformed skin. And the deformed skin is not bone deformed, it is deformed by a tissue simulation. So how do we create training examples that we can actually train on from this? We encode the joint rotations as an array of matrix coefficients. So these are the coefficients of rotation matrices. And then we map that to blend weights. And the blend weights are used in the rest space to correct the shape. So we get something better that is than a bone deformed, like linear blend skinny. This is a more volume-based version of regression. So this is the neural point surface application, which is also a part of Houdini in Houdini 21. So we have points, for example, coming from NPM, and on the right side we see several ways of servicing these points. So how do we create examples to train on from this? The neural point surface application creates local particle information that is stored in a voxel grid, and it maps it to signed distances. And these are the labeled examples that are being trained on. This is the final application of regression that we're going to talk about in this talk. The high-level goal is to go from a low-res 3D voxel grid to a high-res 3D voxel grid. These voxel grids are too big to fit in GPU memory usually, so we split up the voxel grid into subgrids, which we call tiles. So we have a low detail tile that is mapped to a high detail tile. So each labeled example is a combination of a low detail tile and a high detail tile. So I've talked sort of vaguely about creating a function from a bunch of examples. So what do I mean specifically? The goal here is to generalize. So let's illustrate this through our toy example. Here we have a toy example, but we have a model that is not expressive enough to properly absorb the training inputs, to properly fit the training inputs. So this is an underfit situation. So it doesn't even fit the training inputs, let alone the test inputs, which are shown on the right. This is the opposite situation where we have a model that's too powerful, it has too many parameters, so there can be a whole family of wildly varying functions that map the training inputs but not the test inputs. So in this case, we see on the left that we get a good match for the training inputs, but a very poor match for the test inputs. What we want is a well-fitted model, like a more balanced model that fits reasonably well on the training inputs and fits reasonably well on the test inputs as shown here. So that concludes the bit about regression. I hope that makes it kind of clear what regression is. And now I'm going to talk about the machine learning nodes that can be used to create a setup like this. And I'm actually going to mention a few more machine learning nodes as well. So in Houdini 20, we had a collection of machine learning nodes that allowed you to write your own training scripts from scratch and allowed you to run Onyx models. In Houdini 25, we got some higher level tools that just made it easier to do this kind of regression I've been talking about. And also some specialized nodes to help with animation, for example, with the ML deformer. In 21, a lot of the existing nodes got optimizations and upgrades. And you see there's another node to help with machine learning for animation, which is ML post deserialize, which was essential for the post correction. There's a bunch of new training nodes. I'm going to mention ML train style transfer later at the end. That's not a regression node. The rest of the things I'll discuss are all regression. So what are the underlying frameworks that are being run under these nodes? Like the example processing and the dataset I/O are all happening on the CPU. However, the training happens in a virtual environment and runs in Python. It runs a PyTorch script, and underneath it will run CUDA or MPS depending on the architecture you're on. And that will hopefully use your GPU if you have a compatible GPU. The inference works different. It works using Onyx runtime, which is C++. Underneath it, it has an execution provider, which allows you to switch between CUDA, DirectML, or CoreML, which then in turn make use of the GPU. What does a supervised machine learning pipeline look like? What is a typical sequence of steps? Like in the applications we've looked at, there are like certain commonalities. For example, we start by generating synthetic examples, then we augment examples, which is optional. It doesn't always happen. We pre-process examples to make them suitable for training. Then we train those pre-processed examples, and then we can run inference on the trained model. So what does a skeleton setup look like in Houdini? So on the left, we have a sub network. The sub network consists of a part where the labeled examples are prepared. And then the labeled examples go into a raw ML example raw output node. So they get written out as a data set to disk. In the middle, we have a PDG network where we fetch the data set. So that causes the data set from being generated to be generated. Then we train on that. And then on the right, we go into subs again. And we can, for example, load an input and run it through the inference with some pre and post processing. So let's go into the example processing side. To create an unlabeled example, so an input without a ground truth, we can use the ML example node. So as the first input, we connect the input component, and then we create an unlabeled example, which is shown below. If we want to create a labeled example, we simply connect the second input, and we get a labeled example. So our labeled example is visualized as a box, and there's an arrow from the input to the ground truth. Decomposing labeled examples is the opposite operation. So you have a labeled example, you have this arrow, you have this input, you have this ground truth, you pick it apart again. This is all built on packed primitives in subs. So merging examples into data sets of examples is very natural. You use the simple sub merge sub. You don't have to do anything special. If you want to look at specific examples in your data set, you can use the ML extract example node. So this slide was showing it for unlabeled examples, but you can do the same thing for labeled examples. With regression in Houdini, we often learn from a procedural network. So let's say this procedural network is contained in a subnetwork compute target. Then we can feed in a set of unlabeled examples, run them through the for loop, extract the contents of the unlabeled example, send that into the procedural target computation, and then combine it again to form a labeled example. So what we have is unlabeled examples coming out, unlabeled examples coming in, labeled examples coming out. Another commonality is mapping of examples. So this is from the ML deformer example. At the top, we see skeletons being paired with deformed skins, but that's not the representation we need. We need matrix coefficients of rotation matrices, and we need blend weights. So we need to do a conversion. So we go over all these examples, we map the input, we map the target for all of them using a for loop like this. So first we pick apart the existing labeled examples using ML example decompose, and then we combine them again using ML example. A similar idea, but more complicated, is augmenting example. So here we have a for loop, but there's another for loop inside that creates an extra bunch of examples for each existing example. Apologies at the top, there are unlabeled examples, those should be labeled examples. So there should be arrows in them and a box to the right, so I should correct that. In machine learning, you often have invariance properties that you want to enforce. So it means that if you rotate your input, you want your model to give the same output as if you just applied the model to the unrotated input and then rotated afterwards. So rotating before and after should give you the same result. In order to enforce that, augmenting examples is a common trick. So here we basically rotate 4 times around the y-axis to create a greater independence on rotation. Another handy thing you can do with the labeled examples is zipping and unzipping. So the ML example node allows you to zip together inputs and targets together in case you had them stored separately. ML example decompose allows you to do the opposite thing. So once you're done with your example processing and you want to store it on disk, you can use ML example raw. It has 2 multiplying parameters. It has inputs and targets. So inputs can be any collection of pointer attributes or volumes. The targets can also be any connection of point attributes and volumes. So these are being used under the hood to create tensors, which are eventually flattened and put in a data set. ML example import is the opposite. You get a data set from disk and you make it a geometry representation of examples again. So now let's look at some actual ML. So previously we've been talking mostly about processing examples, creating data sets. Not all ML has to be dealing with neural networks. So we actually have some functionality that is not using neural networks, but is still quite useful. So the first of them is nearest neighbor search. So in this case, we don't use a neural network, but for every test input, we look up the closest training input, and we use the corresponding value for that training input and return it as a value. So we get the result that's shown on the right. And for people familiar with Voronoi tools, this looks a little bit like a Voronoi diagram if you look at it from the top. So this functionality is available for the ML regression proximity sub. It works well for low dimension, but the results are not smooth. You would not often use this to create computer graphics results, but it's very useful as a debugging tool if you're just setting up your pipeline. Another classic ML, a non-neural ML example, is linear regression. So here you assume that a linear function is a good approximation of your data. In this specific case, it's not a super good approximation because you see these red arrow bars, which indicate the distance from the ground truth. So this is another node that allows you to do training and inferencing in subs, and it works well for problems that are nearly linear. Then the final classical machine learning approach I'm going to discuss is kernel-rich regression. In kernel-rich regression, we place a kernel function like a Gaussian on each training input, and then we compute an optimal weighted average of these kernel functions. And on the right, we see that the results are a pretty good fit in this case. So training and inferencing happens in subs. The results tend to be smooth with a nice fall-off, and this works reasonably well in low input dimensions. So this functionality is available as the ML regression kernel sub. There's also an ML regression kernel top, which allows you to do the same thing, but exports the resulting model as an ONNX, which means that you can later use it with inference nodes that can use ONNX, which is pretty handy. So now we finally get to neural network training, and that requires the mandatory neural network diagram. So we have the X and Y unit at the top. So this is where the X and Y in the plane go. So I'm using X and Y in the plane here to confuse you guys. And Z is the height here. So on the right, we see a neural network, the way it predicts values as it is at the start, just initialized. So when it's just initialized and untrained, it gives you these crappy results. And now we can see how it gets better and better as we train it. So it gets closer and closer. Not perfect, but close enough. So this diagram is not the exact neural network used for this. Actually, the network that's used for this has a lot more units in it, just so you know. So neural network training for regression is done using ML-trained regression. This is a top node, so it's a PDG node, but its result can be used to do inference in subs. And this can be used in higher dimension than the classical method. When I spoke about the toy example earlier, I talked about underfitting, overfitting. A very important method for or way to prevent underfitting and overfitting is to select the right model and select the right regularizer and select the right loss function. So ML-trained regression has a lot of options to control this. There's the more familiar way that people familiar with machine learning might know. You specify a model, a regularizer, and a loss function. There's also a more versatile way that allows you to connect a lot more custom connections and include a lot more custom steps, which is the one shown on the right, where you only need a model and a state, and you can make any other connections just like you want it. So a partition network, which is the more familiar way, looks like this. You have your input and targets coming in. So these are the inputs and targets you use to that come from your data set. So the inputs go into the regularizer. The input also goes into the model. They give you a prediction. That goes into the loss together with the target. And the regularizer and the loss gets added up together. So there's two ways to specify what your network is with this partitioned approach. There's a way where you can just use a fully connected network, and you can specify the number of hidden layers and the hidden width, and you can use a standard loss, and you can specify a regularizer. But if you need a more specialized model, for example, a convolutional model, there's this option that allows you to specify your own model and your own loss if you want to. So this requires you to know a bit of PyTorch and a bit of Python, of course. But it's only a few lines of code usually. So it's way less code than if you had to write everything from scratch. A unified network would look like this. You have a model and you have a state. So the state contains all the parameters of your model, and they don't necessarily coincide. So some approaches actually have parameters that you train and that get thrown away, so they don't become part of the model. And this model allows you to make more connections as well. So you can first do a pre-processing step before sending an input into the model. You can do all kinds of things here. So a unified network is a single snippet, if you want to specify it. So this snippet is broken up into two pieces because otherwise it wouldn't fit. And don't worry if you can't read this all at once. I'm not expecting you to. This is actually the default snippet if you open up Houdini and put down a node. So all the snippets I've shown so far, you can just look them up because they're the defaults. And they're good starting points to start with if you want to write your own. So that concludes the network specification part. Once you have your network, you can start training it. And there's all the standard options for training networks for regression, including early stopping, validation, everything you're used to, like the batch size. It's pretty standard stuff. There's also a lot of controls over where you get your files from and where you save your files, which is very handy when you do wedging in TOPS to do multiple trainings. Periodic saving and exporting is another very useful option because it allows you to visualize the intermediate progress of your training. So at the bottom, we see the progress for a slice of the volume uprest, and on the right, we see the progress of the ML deformer as time progresses. So now we have a trained neural network. How do we run it? A regression network can be run using ML regression inference. So this makes it very easy to run a model that was trained using trained regression. I'm talking about, I've talked about example preprocessing, but the example preprocessing is not something that only happens when you create your data set. There are certain steps that come back when you do inferencing. For example, when you encode your input, like in the ML example, the ML deformer example shown here, you need to do the same thing with your inference. But there's a funny thing happening when you look at the target side. Like the target side here goes from a deformed skin to a set of blend shapes, but the output of the inference, in this case, is a set of blend shape weights. So you go in the reverse direction. So the mapping you apply after the inference is the inverse of the mapping you apply for the target when you do your preprocessing. A similar connection exists when you look at data I/O. If you look at the node that writes out your data set, ML example raw output, the multiparm that specifies how that works closely corresponds to the multiparm on the regression inference node. And similarly, the ML example import that loads the data set from disk has a target multiparm that closely corresponds to the output multiparm on ML regression inference. So that concludes the training part. And now we can start looking at some applications. I'm not going to go in depth because there's not enough time, but I'm just going to show you some results of the 4 regression applications. So the first one is ML post correction. It can be built using specifically the nodes ML post serialize, ML post deserialize, and ML regression kernel. So here we see the knee joint being corrected. So the red is the original and the gray is the correction. Here's another example of post correction using the shoulder blade. So the shoulder blade is sort of floating and it gets fixed by the post correction. And here we see the toes. The toes are sort of floating in a weird way in space and are getting corrected. Another animation-related application is ML deformer. So the ML deformer recipe that ships in Houdini 21 makes use of the new Houdini 21 armature capture and deform nodes. And it uses ML train regression for training. So let's look at some videos here. Let's show us a spacebar for that. Okay, so this is the capybara. On the left, we see linear blend skinning. In the middle, the ML prediction. On the right, a ground truth. So this is running on, oops. So this is another example, sorry. So this is running on on-scene. In both cases, this is running on on-scene inputs. So these are inputs that were never trained on. So this animation was never trained on. So we see some details that are happening both at the ML level and the ground truth. So this is a video created by Kai, and you may have seen it earlier today. So here the training was not done with the armature, but it was done with a more detailed system of muscles. Right. And it shows you the difference between yeah, this is another one. It shows you the difference between ML deform and using bone deform. So you see the torso twisting, and it's a lot more realistic with the machine learning than it is with the with just bone deform. You see this weird deformation that happens if you go back to bone deform. Yep. Please get me out of here. Okay. So that brings us to the neural point surface that Alexandra worked on. This is available as a subnode. So it has a bunch of built-in models that ship with Houdini. So you can point surface in different styles. So here we see a point cloud that gets surfaced to an SDF. Here we see a comparison between a reference non-neural surfacer and a neural point surface. So you see it's a lot less bubbly. So with conventional techniques that don't use neural networks, they tend to form these bubbles around the particles. Here's another example that uses snow. Again, a reference implementation against a neural point surface. And here's a final one that has a toy. So here the bubbles are really, really clear with the reference implementation, and the surfaces are much nicer and flatter with the neural approach. And then finally, we get to our fourth application of regression, which is ML volume upres. There's a recipe available in SOPs that you can look at, and maybe after this presentation we'll understand it better. A pre-trained model for this, actually two pre-trained models for this are available through the pyro billowy smoke configure recipe. And specific nodes of interest are ML volume tile component, ML volume tile inference, ML volume upres. And again, this uses ML train regression. So here we see a wipe between a low-res input and an ML upres. On this slide, we see on the left side, we see low res, and the right side of the screen, it becomes high res. There's a wispy smoke kind of thing. Here we see a wipe between a flame in low res and the ML upres. You see all the added detail. And here we see it in motion. So a nice thing about this technique is it can be applied to every frame in parallel. And you're going to see more flames in the next talk, by the way. Finally, I want to mention a non-regression example, which is the ML style transfer. And this has interesting applications for terrain. So ML train style transfer is a new training node in Houdini 21 as well. And it's based on a GAN. It's not regression based, but I thought it would be nice to show it as well because it's also a new training node. So here we have a tool where we paint, and then that gets eroded, and it looks, it creates some cool looking mountain terrains. Okay. And here we take a flight over as a rain that was generated. Okay, my next presentation is either not going to be on a Mac or it's not going to have embedded YouTube videos anymore. Okay, thank you so much for listening. Always be on the lookout on side effects content library for ML examples. There's a bunch of ML examples there already, and there's training setups for neural point surface are going to be on there as well. The terrain stuff is going to be on there. There's also going to be a number of upcoming talks about this. There's been a talk earlier today. If you can time travel, you can go to Kai's talk. The next talk is about specifically with the volume upres tool applied to flames. And the Equinox talks are going to be about the volume upres on a more technical side as well. But Jakob and Alexandra is going to talk about neural point surface on Equinox Hive as well. So that concludes my talk. Thank you so much.
or for those of you interested in the Hive Equinox talk, that is happening in the week of September 22nd, so in Toronto. And we will record those sessions as well and publish them if you are unable to attend, but it's a nice opportunity to meet with additional developers aside from Michiel today, because that's held in our HQ city. So anyway, thank you, Michiel. Do you guys have any questions for him? Negative. Okay. Thank you very much.
Your statement says